and the third layer should overflow. To make it easier to get the right depths, some people mark the outside of the cone at the 2.5 inch and 6 inch levels. They don't have to, but it does make the testing more accurate. Okay, he has the first level in the cone. Now rodding. With the rounded end of the rod downward, he rods the concrete 25 times, starting at the outside, spiraling toward the center. And he's rodding deep enough to just tap the base. Now notice one thing. When he's rodding at the outside edge, he holds the rod at an angle, so it's just about parallel with the side of the cone. That's the way to do it. If he held it vertically, he'd miss the edge. It wouldn't get rodded properly. Now he's ready for the second layer. Again, it should reach about half the cone's height. The second layer is rodded just the same as the first, 25 times, starting at the outside and spiraling toward the center. But one difference, he doesn't rod to the full depth of the cone. The rod should go just deep enough to penetrate the first layer by about 1/2 inch. And there's an easy way to make sure the rod goes to the right depth. Just grip the rod at the right distance from the bottom tip, 12 inches for the first layer, 10 for the second, and 6.5 for the third layer. And rod downward until your hand just reaches the top of the cone. Marking the rod at the 12, 10, and 6.5 inch points can help you position your hand quickly and correctly. Okay, ready for the third layer. As I said earlier, the third layer should overflow the cone. The concrete should stay above the cone throughout the rodding. If it drops down, stop rodding, add concrete, then finish with the 25 spiraling strokes. No more than a total of 25 though. And of course, the rod should penetrate the top of the second layer by about 1/2 inch. The cone's full and the rodding is done. The next step is to use the tamping rod to strike off the concrete at the top. The top should be fairly smooth, so it's best to use a sawing motion and roll the rod at the same time. There, level and fairly smooth. The next step is to remove any concrete that has spilled around the bottom of the cone. That's important because any concrete down there will keep the sample from spreading out when the cone is lifted off. Now the cone can be removed. Notice that he places both hands on the handholds and presses downward to keep the cone stable while he takes his feet off. If it's done improperly, removing the cone can ruin the test. Here are the rules. Pull straight up with no twisting or tilting allowed. It should take about 5 seconds. It takes a steady upward lift, slow enough so the concrete doesn't pull on the cone. Now set the cone down next to the concrete, being careful not to jar the plywood base. Lay the tamping rod flat across the cone and measure the distance between the bottom of the rod and the top of the concrete. Measure to the nearest 1/4 inch. You'd record this as 1 3/4. Now here's an important point about measuring. Measure the distance between the top of the mold and the displaced original center of the top surface of the concrete. If a fair amount of concrete falls off or shears away, the test is invalid. Make a new test using another portion of the sample. And that's the slump test. On a stable, flat, non-absorbent base, fill the cone in 3 layers by volume, not by height. Rod each layer 25 times, spiraling toward the center. Strike off the top layer. Clean around the base of the cone. Lift the cone straight up without twisting or tilting it, and measure from the bottom of the rod to the center of the top of the concrete. There's a time limit too. 2.5 minutes between the point where you start filling the cone to when you measure the slump. Always document the slump measurement on the delivery ticket and on DOT Form 319. If the slump is not within the range that's called for, reject the load entirely. But always run a second test before you do. And of course, after the test, the equipment should be rinsed off, especially the rod and the inside of the cone. Then it will be ready for the next time. Now the compressive strength test, casting cylinders in the field and testing them in the lab. Again, equipment and methods are covered in the GHDs. For casting cylinders, GHD 35. First, the equipment needed. Standard cylinder molds with plastic caps, a tamping rod like the rod used in slump testing, a scoop or a blunt-ended trowel, and a ruler. As part of the preparations, make sure that there are enough cylinder molds on hand. You'll need at least 2, and more if the pour will be over 50 cubic yards. The department has approved the use of plastic molds only. Make sure that all molds meet the specs and reject any deformed molds. Measure the diameter of each mold, first one way, then the other. The 2 measurements have to be within 1/16 of an inch or the mold can't be used. Check the length too. One side, then the opposite side. The 2 measurements can vary by 1/4 of an inch, but reject the mold if it's over 1/4. The normal procedure for casting cylinders is very much the same as the slump test. 3 equal layers of concrete rotted 25 times in the same spiral pattern. Remember, the cylinders have to be cast on a flat, level surface. You'll need a random sample of concrete, as you saw in part 1 of the course. Use concrete from the same sample that was used for the slump and air content tests if all the tests are completed within 15 minutes of taking the sample. Place the first layer into the mold, moving the scoop or trowel around the lip of the mold. If the concrete isn't distributed evenly inside the mold, use the tamping rod to move it around. Rod it 25 times, spiraling toward the center. Full depth for the first layer. Place the second layer and rod the same way, but deep enough to penetrate the top of the first layer by about 1 inch. You'll recall the slump tests call for a penetration of just a 1/2 inch. If the rodding leaves holes in the concrete, you should tap the sides of the mold lightly to close the voids. Then for the third layer, overfill the mold, then rod the same way, 1 inch or so into the second layer. Strike off the excess concrete with a trowel or a straight edge using a sawing motion. Then cover the mold with a plastic cap. Mark the cap with the class of concrete and an identification number. Be sure to record the information on the delivery ticket. You have to know where to find the concrete that the cylinders represent. Remember to record the class of concrete and the ID number on Form DOT 319 also. This form is required by the lab and is kept on file for future project information. Cylinders are stored at the worksite for the first 24 hours. And if they have to be moved from the place where they were cast to the place where they'll be stored for that one day, they have to be moved immediately after they are capped and marked. So cast them as close to the storage point as possible. So for the first 24 hours, the cylinders can't be disturbed. During the first day, the cylinders have to be kept on a rigid, horizontal surface that is level and free from vibration or other disturbances. Keep them out of the way. And the air temperature around the cylinders has to be between 60 and 80 degrees Fahrenheit. So in cold weather, find a way to insulate them. After the first 24 hours, and until the cylinders are sent to the lab for testing, They have to be stored in a curing tank according to GHD 35. Place the cylinder in the curing tank with the numbered side up, so it will be plainly visible. Heating elements may be necessary in curing tanks to maintain the proper temperature. The water temperature should be checked periodically. It has to be between 70 and 76 degrees Fahrenheit. As closely as possible, the cylinders have to represent the concrete that is being placed. So the cylinders should be treated much the same way as the actual structure or the pavement where the concrete was placed. The point is, the cylinders must be protected from vibration, damage, evaporation, and high and low temperatures. They have to arrive at the lab in good shape, or they simply aren't going to test properly. Which brings us to the compression test, the lab work. You're not responsible for this phase of the work, but it is good to know what happens when the cylinders get into the testing lab. If you ask the average person what Portland cement concrete is made of, he'll probably think of stone or gravel, sand, cement, and water. But the last ingredient that most people would think of is air. That's right, air. All concrete mixtures have some air, from voids in the aggregates that are trapped in the mix. But nowadays, air is intentionally added or entrained in most concrete to improve its quality. An air-entraining cement or admixture produces billions of microscopic air bubbles throughout the concrete. This makes the concrete more workable, more durable, because it resists the effects of freezing, thawing, and de-icers, and more watertight. And it can be just as strong as non-air-entrained concrete. In Georgia, both the specified and the acceptable air contents depend on the class of concrete. Air content requirements for any class of concrete can be found in the standard and supplemental specifications, such as in this table for concrete structures. The air content test is the most important test made to determine if the concrete is acceptable. As for the frequency of testing, be sure that you run an air content test at the beginning of every placement. And also be sure to run a test whenever cylinders are made or whenever there's a change in concrete mix design. And any time that you suspect low or high air content, run another test. The department allows air content tests by both the pressure and volumetric method. In this program, I'm going to cover only the pressure method, since it's more commonly used. GHD 26 describes the only pressure air meter used by the department, the white air meter. Let's look at the testing method with this meter, the equipment, operation, and calibration. First, the equipment. Before any concrete is brought to the job site, be sure that you have all the test equipment. For the test, you'll need a container for water. A casting cylinder will work just fine. A mallet with a rawhide or rubber head. The white air meter. A round, straight steel tamping rod like the ones used in slump tests and for casting cylinders. A flat, straight steel strike-off bar. And a metal scoop. All of the test equipment, except for the water container and the metal scoop, is usually part of the air content kit stored in the metal carrying case. Now you'll notice that this inspector isn't properly equipped for a safe job. As I mentioned in Part 2, hard hats and safety vests are a part of the equipment. As you take the air test equipment out of the case, check its condition, especially the air meter. White air meters have a pressure-tight base to hold the concrete sample. Be sure that the base is clean, inside, outside rim,